multiply like that, putting the dot in between is good practice. Thus the dot over there. Now, in the case of work, when we actually do this, we will get into, there is an abbreviation for that, but we'll get there. Questions to hear? All right, let's make this look more complicated. Suppose I have a force that is 3 newtons I hat minus 2 newtons j hat, and a displacement that is negative 2 meters I hat plus 6 meters j hat. And I'm doing a dot product. Well, it multiplies the parallel parts. So if I do F dot delta X, I multiply the I components together. 3 newtons times negative 2 meters, which is and I feel confident you can do it without a calculator. You said negative 6? Yep. And then negative 2 newtons times 6 meters, because those are the J parts. And I end up with yep. So in polar form, you got the AB cosine theta. In rectangular form, you multiply the I parts, you multiply the J parts, and add. It is a scalar product, so when I multiply the I parts, I do not have I anymore. The I goes away. There's one other bit that you will need to know. So any questions up to here? What is A dot with itself?
2A?
Then you're adding them.
1.
No.
No.
Let's go to the formula here.
A squared.
Oops, somebody just said it.
A squared.
A squared. Because, looking at the formula here, it's the magnitude of one times the magnitude of the other one times the cosine of the angle between them. Well, what is the angle between a vector and itself? What's the angle between a vector and itself?
0.
Yeah. Times the cosine of 0. Degrees or radians both work. That's 1. So what you're left with is a squared. Suppose I did I hat dot I hat. What would that be?
Squared.
Squared.
Well, the vector goes away. The hat is an indication it is a vector, even though it's a specialized one.
What is it?
But we can do better than I squared. It's the magnitude times the magnitude. What's the magnitude of a unit vector? Sorry, let me re-emphasize the word there. What's the magnitude of a unit vector? Wow. All unit vectors have the same magnitude. unit from the Latin. Uno. We were doing so well. From which the Spanish unos.
One.
Thank you. Yes, unit vector, magnitude of 1. No units, just 1. So I dot I is 1 times 1, or 1. All right. Back to this. Newton's second law, what does force equal?
MA.
So this is the mass of object A times the acceleration of A dot delta x of A. We have A dot delta x. Go through some of the formality here. What is the formula? What is acceleration? By definition.
Change in velocity over time.
Yeah. So change in velocity over time, or change in time, whichever way you want to do it. And change is final minus initial. If acceleration is constant, now what I'm about to do is assume acceleration is constant. The formal definition requires calculus, and you still get to the same place in the end. What is average velocity? Assuming acceleration is constant.
Final velocity minus initial velocity divided by 2.
Close. It's not the difference divided by 2.
It's the sum divided by 2.
Yep. So V initial plus V final divided by 2. And it's also equal to displacement over time. So my dot product over here, I can just rearrange some stuff and stick the mass out there, because nothing to do with that at the moment. And then my acceleration, V final minus V initial over time. So we'll do a delta there. Dot product with my displacement, well, from this right here, my displacement is just this average divided or times time. So this is, I'm going to put VF first. VF plus VI over 2 times time. Time cancels out. The 2 is not really part of the vector, this vector product that we're doing, or the dot product we're doing, so 2 can just come out front. So that's 1/2 mass times acceleration, or mass of A times VF minus VI dot VF plus VI. I'm multiplying binomials here. We FOIL. We multiply the first ones. So that is VF dot VF. So I still have my 1/2 MA, M sub A. VF times VF dot outer plus VF dot VI inner minus VI dot VF outer, or last, minus VI dot VI. Well, VF dot VF is, so I have 1/2 MA times VF squared. VF dot VI really depends on which way it's going. Doesn't, I haven't indicated that they have to be in the same direction or opposite directions. They're not parallel or anti-parallel necessarily. But I have VF dot VI and VI dot VF. Commutative property holds. Those quantities are equal to each other, and we're subtracting, so that goes away. Minus VI squared. I'm going to distribute the 1/2 mass because I know where I'm heading on this. So I get 1/2 MA VF squared minus 1/2 M sub A VI squared. One half MV squared shows up enough that physicists decided to give it a special name or a special symbol. So they decided to make capital K is 1/2 MV squared. And so this becomes K final minus K initial, which is just delta K. Yeah, it is that amazing. We'll actually connect it to the chapter now. Questions at the moment? This thing that we have up here, this force times displacement like that, that has a special name. That is symbolized by the letter W, capital W. The reason why I don't use a capital W for weight is because I'm using capital W for this. So what we have here, more specifically, since we have force is equal to mass times acceleration, that has to be the net force, that's the total force. So this would be the net value or total. So we took all of that and summed it up in this small little notation here. And now the vocab. W, this is work. K, this is kinetic energy. The total work done on an object is equal to the change in kinetic energy. This thing right here, I think it's misnamed, but it does have a name. This is known as the work energy theorem. The reason why I say it's misnamed is it's true because of the way we define work and kinetic energy. It's true because of definition. Ultimately, it's just we combine Newton's second and third laws together to get this. All right, so let's get some of the theatrics out of the way here. There is one formula that I do expect you to have memorized. That 30 years from now, if I run across you in the street, I'm not picturing you homeless or anything like that. We just run across each other while we're on the street. After I remember what your name is, because it's been 30 years, give me a moment. I should be able to ask you, what's the formula for kinetic energy? And you should know it. Now, when I ask you, what's the formula for kinetic energy? I expect, in unison, and I am serious about this, I want to hear everyone's voice. The response is 1/2 mv squared. Don't try to showboat it and say 1/2 times mass times the speed squared. No, 1/2 mv squared. We're going to do this now. This is the chorus of angels I've talked about in the past. What's the formula for kinetic energy?
1/2 mv squared.
Just the guys, what's the formula for kinetic energy?
1/2 mv squared.
The women, what's the formula for kinetic energy? And then all together, what's the formula for kinetic energy?
1/2 mv squared.
That was so nice. That's what unison. Earlier when I was asking for unison, it wouldn't have been cool if it had been like that. It's the chorus of angels that I wanted. So let's think about what's going on here. We have this thing called kinetic energy. Remember I said that the displacements were the same for the two objects when in that particular collision, but the forces were opposite. So in that one case that I gave in class where I had the two colliding and then moving and then separating, well, one of them would be getting positive work done to it, and the other one would be having negative work done to it. But the total work done on both of them is 0. In other words, ultimately, the total kinetic energy stays the same in that situation. Now, physicists, when they ever do any derivation and they end up with some initial amount equals some final amount, or change equals 0, they get really excited. Because this is known as a conservation law. However, conservation of kinetic energy doesn't quite work. Here's an example where kinetic energy is not conserved. Because remember the formula, you just recited it to me, depends upon the mass and the speed. So, what is the speed of this marker right now? All right. If I drop it as it falls, does the speed stay 0? There was a very weak no in the background there, and then a couple of people shaking their heads no. That was a little bit more obvious that it's not the same. Does the mass of the object change? So, kinetic energy is not conserved. So physicists scratched their heads and they said, wait a second, let's come up with something else. I know. As we were holding it up here, it had the potential to do something. Let's come up with something called potential energy. So thus enters potential energy into the mix. The symbol that I use for potential energy is a capital U. I think it's from the German, but I'm not 100% sure on that. I think your book uses capital P, capital E. I will use a capital U. So they said, all right, so potential energy, well, if we think about classical particles, this is classical physics. Objects have a speed. Speed might be 0, but objects have a speed, and they have some position in the world. So speed relates to kinetic energy. Position relates to potential energy. Wouldn't it be nice if the sum of those is always the same? So I start out with no kinetic, but it does have potential, and then as I drop it, it loses potential, but gains kinetic. That would be great. However, this will work. I have a stapler right here, and I'm going to push it. As I push it, it then stops. The position pretty much hasn't changed at all. I mean, position changed that way, but it didn't change this way at all. I had kinetic energy, and then I lost it all. So there seems to be something strange going on there where my kinetic energy actually was conserved there, but not really, because it was moving and then it wasn't. What's the difference between my dropping an object and my sliding it across the table? Because there is a difference between the two. What can you tell me about the forces involved when it falls and when it's sliding across the table?
When it slides across the table, there's friction, and
Okay.
when it's dropping, there's a force due to gravity.
And so they made the distinction. There are some forces which will conserve energy and some forces which will not. Friction is the classic non-conservative. So they came up with conservative forces and non-conservative. There is a formal definition for what a conservative force is. However, I find it easiest at this point to just give you a list of all the conservative forces that we have dealt with in this course so far. Done. Any other force we have dealt with up till now is not conservative. Friction being the classic. There is another force that we will deal with in the course that is also conservative, and so I will throw that in at this point. This is something, we'll actually do one problem in this chapter, but we do it in more detail later on, near the end. Elastic force. Think spring, think slinky. In 152, electric force, magnetic force. And this is the rest, or non-conservative. Now, I do want to point out when I say gravitational force, I am involving both kinds. I'm talking about weight and the generalized force. So we split that into weight and then the generalized. Now, one reason for the distinction here. Every conservative force has a potential energy formula associated with it. We will derive one of them, but I'll just sort of list out the potential energy formulas. Associated with weight is mgh. With generalized gravitational force is negative big G, mass 1, mass 2 over R. Looks a whole lot like the force formula, but it's R instead of R squared. Elastic force, 1/2 K delta X squared. And the other two we won't worry about. Sorry, Amy, if I cut off the shot here going for it.
Just delete it later.
Also, there are 3 work energy relationships. One dealing with the total work, which we've already derived. One dealing with conservative work, and one dealing with non-conservative work. Conservative work is when the force is conservative. Yeah. Amazing. Non-conservative work, what kind of force would you expect?
Non-conservative?
I missed it, sorry.
I said non-conservative?
Yeah, shocking. Yeah. Sometimes physicists label things that make sense. Sometimes. There is a third type of energy, which is really beyond the scope of this particular course, but you might hit it at the end of the second semester course. All objects have mass. And there is an energy associated with mass. This is known as rest energy. Most of you know the formula already, although if I just said what's the formula for rest energy, probably I'd get it blank. But I just start you out, you know the rest of it. E equals, so at least one of you knew it. The only difference you would do is that the rest energy is equal to m sub 0 c squared. It has to involve actually the rest mass. Rest mass is the mass that you have been measuring every time you use the triple beam balance, because it is at rest relative to you. The distinction between rest mass and sort of the effective mass is that as you get closer to the speed of light, the mass will start to increase. The rest mass doesn't, just the effective mass. But that is something for the end of the second semester course. These two combined are what are called mechanical energy. So if somebody talks about the mechanical energy, they're just talking about kinetic plus potential. And everything falls into these categories. Sometimes in chemistry, they'll talk about chemical energy. Well, chemical energy is just a form of potential. Thermal energy is just a form of kinetic. All right, let's derive the two other work energy relationships, and perhaps we can get a problem in, because who doesn't love math? Clever the way I'm going to label this, that's non-conservative. It's not North Carolina. Non-conservative work. I talked about non-conservative work. Well, I actually mentioned conservative work conserves energy. Non-conservative work does not. And so the non-conservative work is just equal to the change in energy. The total work is change in kinetic energy. Non-conservative work is equal to the total change, the change in the total energy. So what I want to do here is we'll start with the work energy theorem. This is the total work. It's equal to the change in kinetic. Forces are either conservative or non-conservative, so the total work is the conservative work plus the non-conservative work. Let's change in kinetic energy. Non-conservative work is just change in the total energy, so work conservative plus change in total energy. Well, I've really only talked about two types of energy. Rest mass would only come into play if you're traveling near the speed of light or it suddenly burst into flames. We're not dealing with that. So this work conservative is equal to the, plus the change in energy, that's just the change in kinetic plus potential, equals the change in kinetic. So the conservative work plus the change in kinetic plus the change in potential energy is equal to the change in kinetic energy. I now got something that can cancel out. I got delta K on both sides. Boom, boom. I bring that over, and I have conservative work is equal to the negative change in potential energy. So I have my three work energy relationships here. So as I drop the pen, the force due to gravity is acting down on it, which is the direction of movement. As I drop this, the conservative work is positive, because the force is in the direction of movement, more specifically, direction of displacement. So my conservative work is positive, which means my change in potential has to be negative. In other words, I lose potential energy as this falls, which makes sense considering our definitions here, because it's gaining speed, therefore kinetic energy is going up, therefore potential energy must be dropping. Let's work through an example and actually derive a formula, and then we can start doing numbers. I take a ball and I drop it. Some mass, it falls. It's going to fall some distance, OH. I'm using this relationship right here. Conservative work is the conservative force times the displacement, the negative change in potential energy. My conservative force is my weight, mg. In the same direction as my displacement, so technically it's mg times my displacement h times, actually I need to change that slightly. This is some initial height, and this is some final height. Get rid of that h there. So it goes from some initial height to some final height. And so this is going to be h initial minus h final. Now the question is, why am I doing initial minus final here? I know that the work is positive, because the force and the displacement are in the same direction. I know my initial height is a bigger number than my final height, so that's why I did it this way, so that this is a positive number. Because I know that this is positive, therefore this better be positive. And that's equal to the negative u final minus u initial. So now we have mgh initial minus mgh final is equal to negative u final plus u initial. Or writing it slightly differently, mgh initial minus mgh final equals u initial minus u final. That's where the physics takes us. So now the question is, what formula can I use for capital U there so that this works? What can I want a formula for U so that this is a true statement. So what is a formula for U so that that is true? Anyone?
U equals mgh.
Yeah. Hey, what a coincidence. If U equals mgh, then U initial is mgh initial. U final is mgh final. And so U initial minus U final is, well, it's that right there. However, there's actually an infinite number of formulas that work. What is another formula for U that would also get you the same result here?